When dealing with stochastic processes, particularly Markov processes, although also other kinds of stochastic processes that we'll discuss shortly, it's very useful to condition on sigma fields in the filtration at different times. Now we have a new kind of time on the block, stopping times. So how do we condition on the sigma field at a stopping time? In the last lecture, we defined the sigma field f tau associated to a random time tau that is a stopping time with respect to the original filtration. Well, in some sense, we already know how to do this. F tau is just some sub-sigma field of f, in fact of f infinity, the sigma field generated by the filtration up to time infinity. And so we know how to make sense of the conditional expectation of a random variable that is either L1 or non-negative on f tau. It's defined by the averaging property. This conditional expectation is an f tau measurable function, and we know exactly what all of those look like from the last theorem in the previous lecture, and is then defined by the averaging property, which is basically the L2 definition of orthogonal projection. That is, if I take the inner product of x with y for any f tau measurable bounded function y, that's the same as the inner product of the conditional expectation of x with y. And once we have that, which uniquely specifies the random variable conditional expectation of x given ft, then we have all the other usual properties of conditional expectation. For example, the Tower property. In this case, using the fact that if I have two stopping times sigma and tau, with sigma less than or equal to tau, then the sigma field at time sigma is contained in the sigma field at time tau, we get that the conditional expectation on f tau of a conditional expectation given f sigma is the same thing in the other order and is just the conditional expectation onto the smaller of the two times. These properties will be useful, but they don't make particular use of the special properties of stopping times. In fact, we will be able to use the structure of stopping times to more delicately understand what conditioning on the sigma field f tau looks like. And here is the proposition that will make most of this work. If tau is a stopping time and x is the usual kind of random variable that we can condition, either L1 or non-negative, then the conditional expectation of x given f tau can be written as the sum over n less than or equal to infinity of the indicator of the event that tau equals n of the conditional expectation of x given fn. These are, of course, disjoint events, and so we just get that this conditional expectation is, on each of these partition pieces of the probability space, the conditional expectation on fn for that fixed sigma field in the filtration. Now, another useful way to put that is as follows. If I define xn to be the conditional expectation of x given fn, defining a stochastic process from x of a special kind that we will spend the next several weeks studying, and here we allow n to be a natural number or infinity, then the conditional expectation of x given f tau is x tau. The process xn, where n is evaluated at the random time tau. Indeed, that's exactly what this sum is equal to. Now, we're going to prove this directly from the averaging property, but in order to use it, at least in the L1 setting, we're going to need to do a Fubini interchange in the end. And to justify that, we're going to start by proving a certain integrability result, which is to say that we need the fact that this sum actually defines an L1 random variable. We're going to show that the L1 norm of this is less than or equal to the L1 norm of just x, to help us do the Fubini interchange later. So let's just compute that. The sum of the expected values of the absolute values of the terms in this sum, well, the absolute value of this is less than or equal to the conditional expectation of the absolute value of x. So that gives us this. Now, tau is a stopping time, and so the event that tau is equal to n is in the sigma field Fn. Therefore, this is a measurable function with respect to the sigma field, and so by the pull-out product rule, we can put this inside that internal expectation. And now, by the usual Tower property, the expected value of this conditional expectation is just the regular expected value. So we'll just go ahead and remove that. But that is a sum over partition of the entire probability space of the expected value of this random variable. That is, it's just equal to the expected value of that random variable, which in this case that we're interested in is finite, as we were hoping to prove. Now, it follows from there that x tau is also an L1 random variable. And that's just because x tau is equal to the sum n less than or equal to infinity of the indicator of the event that tau equals n, xn. And so therefore, the expected value of the absolute value of that is, by the triangle inequality, less than or equal to this, which is, as we just showed, less than the expected value, the absolute value of x, which is finite. That is, we've proved that x tau has L1 norm less than or equal to the L1 norm of x. This, by the way, is a bound of independent interest that we will reprove again later in the context of martingale inequalities. Regardless, with that regularity property under our belts, we want to show the statement of the theorem, which is that conditioning x on f tau just produces x tau. And to that end, using the averaging property, let E be any event in the sigma field f tau. Let's compute the expected value of x integrated against the indicator function of E. Again, we'll just use this partition of the probability space, which means, using the fact that x is L1, or if x is positive, just following by the definition of probability, that this is the sum over n less than or equal to infinity of the expected value of x times the indicator of E times the indicator of the event that tau is equal to n. So we can just combine that here with the intersection with E. Now, E, by assumption, is in the sigma field f tau. And what that means precisely is that E intersected with the event that tau is equal to n is in Fn. Well, therefore, by the averaging property for the sigma field Fn, this expected value here is equal to the expected value of the same product, but with x replaced by the conditional expectation onto Fn. But that was our definition of xn. And so putting all of that together means that we can rewrite this sum as the sum n less than or equal to infinity of the expected value of xn times that same indicator of the intersection of E with the event that tau equals n. Now we can untangle and write this again as the indicator of E times the indicator of this set. And now finally, we can interchange the expected value and the sum And this is where the calculation we did at the beginning of the proof comes in. If x is L1, we showed that this sum is absolutely convergent, and so by Fubini's theorem, we can do the interchange. If x is positive, and so all the xn's are positive as well by the monotonicity of conditional expectation onto Fn, then this just follows by Tonelli's theorem. And once we have it in this form, this sum is again exactly equal to x tau, which shows us that for any such set E, this inner product is equal to this inner product here. Since we know this is f tau measurable, it follows by the averaging property that x tau is the conditional expectation of x onto f tau as desired. So to reiterate, conditioning on f tau can be accomplished by evaluating x at tau, where x is turned into a stochastic process by defining xn to be the conditional expectation of x onto Fn. Again, we will see shortly that this kind of stochastic process here, which is called a martingale, is going to be the bread and butter of many of our calculations throughout the rest of this course. Now, we're going to give one application here before we head that direction of this formulation of conditioning onto f tau, and that is in terms of a handy new reformulation of the Tower property for conditional expectations. Again, if we have a random variable of the kind we know how to condition, either L1 or non-negative, and measurable with respect to the big sigma field for the probability space, and if we have two stopping times not necessarily comparable with each other, sigma not necessarily less than or equal to tau or vice versa, then we have the following two technical properties that are easy to calculate, as we'll see in a moment. If I condition x on f tau, then on the event that tau is less than or equal to sigma, that's the same thing as conditioning x on the sigma field at time minimum of sigma and tau. Similarly, on the event that tau is bigger than sigma, the conditional expectation of x given the sigma field at time sigma is equal to the conditional expectation of x on the sigma field at the minimum of sigma and tau. And from those, we derive the following useful consequence. If I condition on f tau and then condition on f sigma, that's the same as conditioning on f sigma and then conditioning on f tau for any two stopping times. And in both cases, what we get is just the conditional expectation given sigma min tau. Let me emphasize once more that this does not require that sigma is less than or equal to tau or tau is less than or equal to sigma. It holds for any two stopping times. And this is quite interesting and unusual from our intuitions so far because, well, first of all, what is this thing, the sigma field at time sigma min tau? On your homework, you're going to show that it is the intersection of the two sigma fields, f sigma and f tau. But this is a special property because, in general, we do not have the property that the conditional expectation on G of a conditional expectation on H is equal to conditional expectation on G intersect H. That is generically false for two sigma fields. This is a special property of these nice sigma fields here. So we're going to prove property 1. Property 2 follows almost exactly the same way, so I'll leave those details to you, and then we'll prove property 3. For property 1, we'll just calculate the left-hand side here. Well, we'll use the expression from the previous proposition that this conditional expectation is equal to x tau, where xn is the stochastic process given by conditional expectation of x given fn. In other words, we just expand over all possible values of tau, summing the expected value of x given fn. And now let's look at this product of two indicators here. This is a 0, 1 valued random variable. It's equal to 1 if tau is equal to n and tau is less than or equal to sigma, and it is 0 otherwise. And a nice way we can write that, alternatively, is as the indicator of the event that the minimum of tau and sigma is equal to n and tau is less than or equal to sigma. Indeed, in the event that tau is less than or equal to sigma, tau is the minimum. And so we can simply replace this product of indicators here by this indicator. Then we can factor that as the product of this indicator and that indicator and pull this one out. And now using again the previous proposition, this is exactly equal to the conditional expectation of x given f tau min sigma. That demonstrates property 1, and again property 2 is very similar to prove. So now let's use those properties to prove property 3 about the effect of conditioning on f tau and then f sigma, or vice versa. So here we're going to use the following facts. First of all, that f sigma min tau is actually the intersection of f sigma and f tau, and moreover, the two events, that tau is less than or equal to sigma and that tau is greater than sigma, are actually in this sigma field. That's on your homework to prove. Using those facts, if I take the conditional expectation, let's say in the order f sigma following f tau, well, outside the first but inside the second conditioning, let's just use this partition of the probability space into those two complementary events and break up that sum accordingly. Now in this first term, inside here, by property 1, this is equal to, on the event that tau is less than or equal to sigma, conditioning on f tau min sigma. Now by the result stated here, that's on your homework, this event that tau is less than or equal to sigma, that is in f sigma min tau, which is contained in f sigma. And so that means that inside here, we can pull, once we've done this, that outside the first conditioning by the product rule. Similarly, this event is in f sigma min tau, which is contained in f sigma, and so by the product rule, we can pull this outside as well. And so combining those steps together, we get this sum here, the indicator of tau less than or equal to sigma of this double conditioning, plus the indicator of tau greater than sigma of this alternate double conditioning. Well, here we can just use the Tower property, since this sigma field is contained in that one, to write this as the conditional expectation onto the smaller of the two. And as for the second term, by property 2, on the event that tau is greater than sigma, this is equal to the indicator tau is greater than sigma of conditional expectation onto the minimum time. And now we can do the same thing. We have a double conditioning here, but this is a larger sigma field containing that one, and so by the regular Tower property, this is equal to conditioning onto f of sigma min tau of x. So I have the same term repeated twice here. Here I have indicated that tau is less than or equal to sigma. Here I have indicated that tau is greater than sigma. Those together form a partition of the whole probability space, and so when I add them up like this, I just get the conditional expectation of x given f sigma min tau. So that's half of the desired statement. This is where we condition on f tau and then f sigma. But of course, the result is symmetric in sigma and tau, and so just reversing the roles of sigma and tau in this entire proof proves the result for the other ordering as well. And that concludes our proof.